Hi, welcome to the Endpoint Podcast. I'm Raz. This is my chief architect, Isaac Zhang, and the CEO of Succinct, Uma Roy.
Hi, thanks for having me.
Yeah, thanks for being here. Today, we're talking about how we bring the Web 2 experience to Web 3 but still keeping it verifiable. We're going to talk about two of our new white papers that are coming out on vApp, which is a verifiable application, and QMDB, quick Merkle database. To start, can you just give us like a background on ZK and what drove it?
Yeah, so it's Succinct. We're building a ZK VM called SP1 that's super fast for making all computation verifiable. What ZK lets you do is two things. First, it lets you prove to someone that an execution or a computation happened. And the magical property is that they can verify the result of that computation in much less time than it takes to re-execute the computation. So that's the verifiable part. It also is magical because it lets you hide what the inputs are to the computation. So that's kind of the privacy angle of ZK for those of you who are familiar. And yeah, those two things combined, I think, are super important to making all of crypto and blockchains actually scalable and also adding privacy to them.
Cool. I guess today, it's like we have you on this podcast. We're going to talk about some of the newer research that we've been working on that kind of takes advantage of the ZK tech and potentially FP1. But I guess the overarching view of this whole conversation is about how we make a Web 2 experience on Web 3, something that has that snappiness, that quick reaction that anybody can access it, millions, hundreds of millions of users, and is verifiable and secure like a Web 3 application. And so today we're going to go over two new pieces of research that we've been working on here at LayerZero. One called vApp, which is a verifiable application, and the other is QMDB, which is a new type of database. It specializes in being able to Merkleize after every single transaction, which has strong properties for ZK. So I guess with that, Isaac, you want to speak a little bit to that and talk about it from that landscape?
I think it's better to start from again. We're talking about the recent advancement, like people's attempt on this, like a sovereign that and bullet thing. It'll be better for you to talk about this.
Yeah, I think if we look at the history of ZK, maybe to take like a even bigger step back, I think we've all kind of agreed that like the end game of any blockchain is like you post data to this like decentralized layer, and then you prove verifiability of like all the transactions that are happening. This is like Ethereum's rollup-centric architecture using a ZK proof and then verifying it on a base layer like something like Ethereum. And then once you use ZK to prove the state root, which is like a commitment to that rollups world, then you can do things like interoperability, bridging, withdrawals, stuff like that. And I think people have acknowledged like ZK is very needed for scaling all of blockchains like from day one. I think it's like such a perfect fit because in a blockchain context, you have everything that's decentralized. So if things are decentralized and many people have to re-execute computation, that's why there's so much overhead. Now, ZK solves that problem because you have one person who's generating a proof of a computation and then everyone else verifies it and they pay much less. Like verifying is like basically constant time and they don't have to re-execute. So I feel like for me, ZK, that's why ZK is so fundamental. It's this like compression of computation, as Raz has been saying, and why it's so fundamental to scaling blockchains and getting beyond the limits we encounter today, or at least some of the limits we encounter today. I guess like the history of ZK is that everyone's been like, oh, ZK is super important, but it's always been like super hard to use. You had to write like custom circuits. You had to like write your computation you wanted to prove and like basically these assembly-like languages. It is very primitive and that sucked. And then you have a ZK VM like SP1 where you can just write normal code. So you just like write Rust. And then we prove the execution of Rust compiled to RISC-V, which is a special instruction set. And by being able to prove any program written in any normal language, that's how you can kind of get this vision of what Roz was saying of a verifiable DAF. Like you can take any decentralized application, whether it's like an exchange, and that's like probably the biggest one, but really anything else. Like it can be like a borrow lend rollup. It can be like even like a Web 2 application that wants some verifiability. You can just stick that normal code inside a ZK VM like SP1 and then make it verifiable. So yeah, I think that's like, when I hear about verifiable dApps, I feel like the key, it's an interesting thing to look at right now because we have ZK VMs, they're working, they're live, and they kind of show this path to like proving any commutation. So that's maybe an interesting time for why it makes sense for you guys to be looking at it right now.
Can you help profile where we are or in terms of like a CKPA adoption and the technologies?
Yeah, there's this like kind of like Moore's Law DK, I like to say, where let's look at SP1 as like a super concrete example. We first launched SP1 in like February maybe of this year, and at that time it was maybe 80 to 100 kilohertz. So like it can prove, you know, programs at a rate of like 100,000 instructions per second. That's like a really, really bad computer from like the 1960s or something. And since then, we've been able to crank up performance by like more than 10x. And now we're at the point where on a single GPU, we can get speeds of up to like 2.5 megahertz. So 2.5 million instructions per second. So the curve of like performance is just like up and to the right. And it's on like a very promising trajectory. And I think that trend is basically like only going to continue like next year and beyond.
Do you see a clear path from 2.5 megahertz to like what more modern CPU have like a 4 gigahertz of how a clear path?
I don't know. I don't know if we'll ever get there on like a single machine. Like obviously I think ZK is gonna have overhead, like no matter what, right? You're like, you put in a lot of extra effort and like a lot of extra computation, but to generate a proof of a computation. But the reward you get is now like 1 million people or like 1 billion people can just verify the same thing. So like I think there is like probably some law of physics that says like we're never going to be able to run at the same speed as like a CPU on a single machine. But I do think by like throwing a lot of parallelized compute at it, or by like making special hardware, like I think if you stack like better proof systems, better engineering, specialized hardware, and you stack all those things together, you could probably get like a pretty specialized system that maybe the cost is like 1,000x or 10,000x the cost of normally doing the computation from like electricity perspective, but it ends up generating a proof. I am optimistic we could get to that point.
What about like specialized hardware like ASICs or FPGAs? Like, does that get us closer to having what speed of a CPU line rust or something?
Yeah, for sure. I think like that will be one very important ingredient to getting ZK to be both more performant and also more cost efficient in the end game.
Interesting. So that's the 10x on the tech side, right? So what will be the 10x on the adoption side? Hope so.
Yeah, I think like the tech, honestly, even these days is already in a pretty good spot. I don't know if you guys like saw our latest OP statistics numbers where we take OP star, we stick it in SP1 and we run it and we make a full ZK rollup. But I think the cost per transaction for proving like an ETH transfer is like a couple hundredths of a cent of proving cost. And like a DEX swap is like a couple tenths of a cent. So it is actually already really, really cheap. Like for those transactions, you're actually paying Ethereum more for DA and like blobs when the blobs are like on target and being used. So I think already today, like ZK is actually pretty economical. Now that is kind of the case because like the other parts of the system are like still pretty expensive. Like Ethereum blobs are still, you know, pretty expensive, and they're in the next hard fork, they're like thinking of raising the number of them and stuff. But already it's pretty economical. So I think the adoption problem is more of a social issue right now than a technical issue. Like I think there's a lot of teams and systems that have like gone to market early with fault-proof technology, and to be fair to them, like upgrading their entire protocol to ZK is a really big lift. And I'm sure that's even true for you guys. Like a few years ago when you launched LayerZero, ZK tech sucked and it was impossible to have a ZK-like client. And actually that's like kind of where we got our start. And yeah, so it was really difficult. And now ZK tech's like very easy and it's ready and it's cheap, which is awesome. But like upgrading like fundamental parts of your protocol that are really security critical just does take a long time. And so I'm very confident the tech is ready and we will get there. It's at this point more like a social issue than anything else in my mind.
We've seen different forms of ZK application, that is ZK EVM, right?
Yeah.
If we polarize that to the extreme, what would be the ideal ZK runtime app look like?
Yeah, so I think what you're kind of saying is today, most of the things people want to prove in ZK are just like these ZK EVM rollups. And actually, so we've done that for Optimism, which is a ZK EVM. We're working with some other teams on their ZK EVMs. And now we have some other teams building like ZK SPM, ZK, move ZM on us. But I think what you're suggesting, and I've kind of like tweeted about this, is I think the end game is for very, very popular apps, you're going to go direct. Like instead of having a general purpose chain where you have, a runtime and then people deploy Solidity contracts onto a ZK EVM, for a trading app, you could imagine that you have just your application logic, like, matching trades or orders or, proving clearing price, stuff like that. And you just have dedicated block space that's verifiable for a particular application. And I think that's like what you guys that is like the direction you guys have been thinking with like this verifiable app concept. I think another name that people talk about often is like app specific rollup or like app chain. So I think the app chain thesis is super correct in that like you have all these ZK app chains everywhere devoted to very specific block space.
Yeah. And the reason we call it like a vApp, a verifiable app, is that just to compare with vApp. It's at the end of the day, it's just another way to write something that's verifiable with decentralized applications. Do you want to talk about?
Yeah. So one of the things that kind of, I guess, taking a step back, what drew us into ZK, one of the things that we do here at LayerZero is we're always researching the latest and greatest early. And so actually when Succinct entered the bridging game, that was our first taste of, ZK's starting to get pick up. We need to learn everything there is about it. And so, but ZK made a lot of sense in terms of compressing compute, like you talked about earlier. Like one big computer, big machine is doing all this computation, and then these smaller machines are verifying. You can have like the layer 1 of Ethereum do very little compute to verify a large amount. And like, when does that unlock? And from our perspective, and we started diving in, well, what could we do with this? And come up with a lot of ideas, but the one that we thought would make a lot of impact and could be really useful would be this concept of verifiable apps, because you could almost imitate anything in the space. PayPal, for example, could have all this other stuff that happens within PayPal that has nothing to do with blockchains or securing anything. That doesn't need to be in the back. And only parts of it, or sort of like transfers or account management, could live in like a sidecar that is the vApp itself, and that be verified on Ethereum or some other type of L1. And to us, that's super compelling. You could do things like cron jobs and time-based. Since you control the execution environment, you can do much more than DApp. You don't with a DApp, you don't control that, so you have to work within those bounds of when you get called, you can do things. Versus you could run things always on a DApp and give an experience that the general public is used to with all this amazing Web2 technology that's out there, but with the security properties of Web3, which is what has drawn a lot of people to the space in terms of owning your own assets and not being able to be robbed, for example. So yeah, like that's the vision. And then when we think about things from bottleneck scammer, right? Like there are free components to like layer 1s. So it's like network, compute, and storage. UV. And a vApp solves network, because now you only run it on a single in sequencer, right? Or compute. And the compute is solved because now you're running a ZK proof of building a ZK proof that goes to this layer 1, and you can now have a beefy computer, also an application that does all of this split, like kind of Web 2 feel, and does all this massive compute, builds this ZK proof and puts it to the actual layer 1 that's securing. And then it leaves the last step, which we'll get to later on today, which is, well, then your bottleneck becomes storage. And using like an MDT proof is any type of existing databases that are out there, like MDT or Virgo or anything else, is very expensive to localize after a transaction. And so then this becomes your bottleneck, even for that, when you're trying to mimic what Web 2 is.
So, okay, can I have a question? So, given that, assuming we have in like a really scalable amount of like a ZK compute, what will be the ideal properties for any data layer storage space for that?
The ideal properties are that localization of the DB and the database is like very, very efficient in ZK. So yeah, right now, like for an Ethereum block, we spend a lot of time, basically Merkle proving the state so that then we can like verifiably do computation with the particular state of the world. And yeah, making that a lot more efficient would mean that we could prove the execution of all this stuff a lot faster.
Yeah. So we talk about, like, I know that you guys recently done something pretty cool called OP Succinct, right? Would you like to talk about the architecture and how that it basically increased the verifiable TPS to infinite?
Yeah. So today, basically, you have like Ethereum, and you have blobs of data that are like posted. So these are blobs. And you have a rollup that has blocks. So maybe these are the blocks in the rollup, and they're getting posted to blobs on Ethereum. And then with OP Succinct, basically, every so often you want to be able to like prove that the state of the rollup after executing all these blocks is a certain, certain value. So you have like a bridge contract on Ethereum, and you have like the rollup state root. And as you guys know, the state root is like the main key thing for depositing and withdrawing, and proving state and making it interoperable, making this rollup and chain interoperable with other rollups and chains. So in OP Succinct, like how it works is, okay, and then maybe to start off with, today with the optimism stack and fault proofs, this state root takes 7 days. And there's this like complicated system where like the state root is only finalized after 7 days, which is really bad. Because like you can only have the interoperability after 7 days. And there's like techniques and hacks around that, but like that's not the nice. With ZK, what you can do is you can just generate a proof for a range of blocks. So I take a range of blocks, I start generating a ZK proof of it. And that maybe takes some time. And then I have the next range of blocks. I'll start generating a ZK proof of it. And then basically every hour, so these proof generations take like, minutes, maybe like 10 minutes for any block. And then every hour, I'll take them, I'll aggregate all these proofs together, and then I'll get like one aggregated proof. And then I'll post it to this contract, and I'll update the state root. And then the 7 days goes to 1 hour, which is a lot better. And so, yeah, Isaac, I think, had some questions around like, okay, well, how much TPS can this whole construction do? And actually, the fun fact is this can basically support like an unlimited amount of TPS. And the reason is like, basically, like, say my blocks are super full and they have a ton of transactions. We can just prove a lot of ranges of blocks in parallel. So we can just scale the number of machines we use here. And the number of machines we use just like goes up. And we can scale the number of machines to kind of scale with the TPS of the chain. And it means that we can basically have like arbitrary verifiable TPS on this chain and still have like 1 hour finality, which is pretty awesome. And yeah, also a big priority for us is also improving the latency. So, right now 1 hour is actually bottlenecked by Ethereum because like you don't want to be posting proofs to Ethereum very frequently. That'll cost you a lot of gas. But you can imagine a world in which like we have proof aggregation, Ethereum's gas costs go down, they scale to L1, all the fun stuff our friends were talking about. And another big effort for us internally is like lowering this latency and making proof generation a lot faster to be close to real time for proving blocks in a change.
So with the latest SP1 board version, right? So what are we talking about the latency here and for how much gas in the EVM block?
So today in SP1, to throw out some numbers there, I think a 15 million gas Ethereum block takes around, and this is going to be really, really rough. You might find some, examples that are different. It takes 300 million RISC-V cycles. So, and RISC-V cycles is basically the number of RISC-V instructions you need to like actually run to do this computation of like processing transactions and stuff. And currently on a single machine, we're able to do around 2 to 2.5 million cycles per second. So, okay, you guys can do some quick maths. 100 seconds. Yeah. So that ends up being, a couple minutes, like a little less than 2 minutes on a single machine. And this is like a very good, like 4090 machine. If we parallelize across many machines, we can get to, in a theoretical model, around 30 megahertz. 30 million cycles per second. Now, this comes with some caveats, like, your program has to be long enough and like all this stuff. But you could imagine that we're starting to get to proving an Ethereum block in like tens of seconds.
Can real time proof.
Yeah. And so an Ethereum block today takes the block time is 12 seconds. So you could imagine that and again, this is an idealized model. Maybe by the time this comes out, we'll be closer to that. It's like more of an engineering problem than a theoretical problem. We can be pretty close to proving an Ethereum block at Go5.
Yeah. So ideally, I can just, cut them in half, right? Or make the block smaller, or compose a small block with just 2-3 transactions and make the gas smaller and then reduce the latency. Is that possible?
Yeah. So like the smaller your block, like if your block is 1 million gas, there will be less cycles here, and then you'll be able to prove it even faster.
So Isaac, can you introduce to us what is the current state of virtualization in the database, like with like Ethereum, VVG, like the cost of that? Can you kind of just walk us through?
I think different shade, they have like a different implementations, even like a different execution client rate. For example, on Ethereum, the gas and the ref, they have different implementations. They have different DB selections, even though they're tri-structures sync.
Because they help to build the MPT tree.
The MPT tree. So to put it simply, like with a simplified model, it's like a 2-layer architecture. Right now, you build like the MPT as they on a box BV, right? Which is the tree itself, even if it is design, right? So every single read, if you don't need to go through the tree search process, it will be like a log-n search pause. And but that would be added to the VoxDB itself, which incurs another log-n search cost, depending on the implementation. And there are many teams doing very innovative works on the NOMT and MonadDB, trying to merge these two into one layer to, like we call it a disk native format, which is binding the locality of the tree, the vicinity of the nodes into the disk layout, right? So that would make them like a more native, basically to reduce the write and amplification of any updating behaviors.
And so they're trying to preserve MPT and they say, instead of making a new tree structure, let's just try to optimize MPT for the.
So if you want to keep the Ethereum compatibility, right, and reducing the write amplification is the best thing you can do. And by write amplification, we mean like when you update a value, your intent is to update one node, right? Because you update 10 nodes or 20 nodes, depending where you are on the Merkle tree, and depending where they are stored on the disk. So that's the undercaching. The 10x, the 100 is huge, which makes democratization process become IO bound. Yeah, the disk, when you, in a lot of chains today, if you scale up the TBS, do a penetration test, the disk is always the first one to break. And can we lift that limitation? Can we eliminate that like a scaling blockers? And what will be the Desperate theory? So we'll be searching for this line of design for in the last few years and observing the changes and new ideas in the field, right? But we always look at invasive repeatability, the simplicity and elegance of the design, the simpler, the better, right? So it's like one of my favorite designs is actually door stop. The door stop down, the triangle stop and stop the door pushing through. It's so simple, intuitive, and it's easy to understand as you apply more pressure to efficient increase. So it's a very adaptive process. And the way we think about it is like, can we design a software thinking from the first principle of the hardware characteristics, right? As I was saying, if the more physics you have, the less engineering you will need. Is you utilize something that natural to the system, like a universal properties. So what will be a native tree look like in practice in the design? So what will be the desirable properties that we have? So if we cut out the QMDB into its basic interfaces will be, am I blocking the screen? No, so it's reported. So you have like a read, you have write, and then after that you have modularization. Some chains decided not to do more modularization, but they don't think they need like a blockchain. They don't have like a multiple. They have transferred a no multiple. And even Solana, they do like an organization after about 2 days. It was fine back in 2017, but it's increasingly more required.
It was originally for Litecoins.
Yeah.
And Solana decided they didn't need that. I mean, it wasn't like a property. They were a sacrifice of Litecoins for speed. But now with the Pod L2 Asia ZK and L2s not having a Merkle readily available to do not just their accounts, but all the state, limits their ability to take advantage of ZK and their twos.
And it would eventually limit the overall throughput of the ecosystem, right? And not just that, the Merkle would give you really amazing properties. Like you can probably use some atomic state read from L2 on the L1, without which you cannot do it. Okay, so, and what would be the cost for these passes? For this design, the naive design, it will be like a read. If you store 2 subdata on KV, like a pure KV, the read could be like a log n. Right? And for the write, it will be more predicting that. The write itself will choose the old log n nodes. And then on top of that, you have the database.
Can you give us a little more detail in that way? Like, what are the operations that are happening? Why is it so expensive on Ethereum?
So actually, at the oldest version of Ethereum clients, when you do a read, you need to climb like a search through the tree to find out the node with the key, right? But then the latest implementation for this can just store non-self data, so you can do directly read without searching through the tree. But when you update it, you still need to propagate changes to the Merkle nodes of the tree, right? So they
Optimized tree, but they couldn't optimize right.
Right, and because the cost of write is very intrinsic to the triad byte.
Yes.
Yeah, so it's the data structure problem, not just some storing and other self data problem. And then the Merkleization just make it worse because it will involve more nodes read and write. Yeah, and you eventually become a scaling problem. In theory, you can store everything in the memory, like you will be memory bound, right? You could either store all the memory, like all the data of Ethereum data into memory. It's definitely not scalable, especially talking about this data bloat, right? And stay bloat. Then what will be the desirable property of that? So we managed to find a design that reached following properties. So the read is just one disk with IO. That's like a theoretical minimum. For the write, we have a capacity of in terms of disk IO, the O1, the constant curve cost that allows us to scale the INOPS utilization, the throughput of the disk layer with the BD machine nearly linearly. And then for the localization, that's like a very interesting part. Others trying to reduce the write invocation to a lower value. We actually reduce it to 0. We don't do any state like at this read and write. So we don't do any this read in word localization at all. It's purely in memory. And how to do it? So the high level design is very straightforward. Like we try to fully explore.
Before you go into this, like the actual approach here is most people are saying, let's take MBT and optimize around right? Because every tip that given the MBT is a requirement. And we want to say, compatible with the Ethereum, or others just say, F it, we don't need Merple, right? We don't need proving. And our approach was, let's take away all these assumptions. Let's try to optimize for the hardware that's running on. And he built a database very specifically built around SSD flash. Yeah. And so that is why these numbers seem outrageous, is because it is an optimized database for that.
I think Steve Jobs says if you really care about your software, you should design it in hardware, right? So if you really care about your database, you should think from the hardware perspective, move that upfront. They were built into the hardware itself. And the high-level design is like, so SSD has like amazing property, really high throughput, slightly high latency, and it's very great at parallelized read and sequential write. So we designed data structure inspired partially by the Merkle Mountain range back in the days. Used with append-only architecture. Every single state change or readation, you will create a new entry in the tree. So conceptually, it's like infinite large file, and you keep appending to it, like one method at a time. And then the tree is not tried, so like a balanced Merkle, like a binary tree that we index with the sequential number before the index, right? So because 1, 2, 3, 4, 5. We don't search to the key value. And then we build the balanced binary tree, pop that all the way to the Merkle root. This upper tree part does not store any word state. All the word states live on the disk. Okay, and then that's why when you localize it, you don't need to read any of this data. Everything is in memory, and it's like very small. You only have the tree node, the intermediary upper tree doesn't include any word state. It doesn't incur any disk read at all. That's why it's fast. It's like incremental editing. And this upper tree is like a memory buffer on top of a disk matrix layout, and as you keep appending to it, right? And then we have another structure called a tweak. Basically, it's a collection. It's a unit for you to compress the memory footprint. In our current setting, we have 2048 nodes. This is not the binary tree within storing the actual state value, right? And when this tree is full, because it's append on, when it's full, the Merkle root becomes immutable. Then when you try to localize, you don't need to read anything from the eval. You can memorize basically the Merkle root of. That's why it is so disk efficient. You don't need to read all values. And when you keep updating it, all the changes concentrated on the tail part of the tree. So a large part of the tree remain intact and changed, so you don't need to touch them at all. It just keep moving forward. So every single tweak as the life cycle of the tweak is coming from the background. First, it would be fresh when it just initiate it with no value, right? And then you appending to it when you saturated the 2048 values and becomes active but not fresh. And when all the data are invalidated through compaction or like a state update, it becomes inactive, and over time it can be pulled from the archive, from the full node. If you want an archive node, you can just archive them as well, all the way from the genesis to the late state.
So I know the answer, but you sure be also wondering, when you make an update, so you'd say you update a state for balance, it's smaller. How do you know the history? How can you follow it, right? If everything's put sequentially, it seems that is an expensive look.
Yeah.
Tell me how.
That's an interesting question. So with that, so this is the actual physical disk layout. It's an infinitely large file. You keep appending to it. And then we have a lot of indexer design. Basically, it's like a database thing. Indexer give you a view of the full history. If you only care about the latest value, then which need to maintain an indexer to keep track of the latest value, that would be applied in the full node. If you want to have the full history, where there are changes, which block height, and you need an archival indexer, which is more expensive to do it. And then that, like a full indexer, we can add even sort of a design trade-off in terms of like memory and SSD footprint for different purposes, for different types of nodes. And then like it's interesting, like another very important property for QMDB is that like it's not just disk friendly, but it's also very memory efficient. By that, I mean, every single entry seems like a lot, right? You need index all these things. But for an efficient in-memory indexer, the overhead, the memory footprint per entry per state is simply the 15 to 16 bytes. That's the really small footprint compared to all the other implementations. And fundamentally, because we don't need to index the value itself, we index the location of the file, which is like a really short value compared to the 32 bytes value on EVM, or even larger value on Solana account, like 10 megabytes. So the things when you index are very short by nature, right? And this is not even the best. We have something called the hybrid indexer, which is to optimize it further, to push the data into ISK. So when you do read the indexer, you would incur some extra disk I/O, but still constant function cost. And you can reduce that to about 3 bytes per entry. And this is a very amazing value because we can counter the state blocks, right? With probably like a billion. I think the last time I checked, Ethereum right now has approximately like 1.5 billion slots. And 3 bytes per slot could be just like a 5 gig RGB RAM. Still enough to index all the Ethereum there. Right. And but then the cost will be like a 50% trade-off of the performance. But the performance is like a massive, right? It could be, some people would say it's overly proficient, so we can make that trade-off. And that gives you a lot of big flexibility and liberty from the node side. You can introduce the really small nodes into the blockchain that has really low hardware requirement in terms of both disk and memory, and can still produce blocks really quick. Yeah, and being the SSD native or friendly and memory efficient, there's like one property and two property. It actually has some other emerging property that the industry had never seen before, or in production, which is a full history proof. Full history proof. Because the Merkle root is append only. So anything that have happened in history, living there. So not only you can prove the state, the inclusion and exclusion proof of any value at the latest state, at the tip of blockchain, you can actually prove anything that happened. And then you can have really novel use cases. Say, I can aggregate the T-wall price of any assets of Uniswap fee at the latest block. You can provide proof, and then you can get the value just this
on the same blockchain.
On the tip of the blockchain. There is something emergent like that, and you would just open up a huge surface of design space for you doing this. Yeah, and you can change the granularity to arbitrary. Okay, you can T-wall by hour or by minutes, right? If you were to buy that logic specifically, you need to buy a lot of data, right? Do a lot of computation. But now you don't need to buy those things. As long as you have a price point, you can aggregate it data up. This is amazing thing, and it in return reduce the unnecessary data right to the blockchain, just to store this computationality, which could be aggregated later with that pool. So, conclusion 1, 2, 3: super low disk I/O that allow you to scale nearly infinite machine, memory efficient to reduce the hardware requirement to allow even super small home sacred node to become very efficient in running like a large volume TBS. Zero disk I/O workalization allow you to, it's basically to make it very super CK pen in that case, for example, the OP Succinct architecture and U property full history proof. That would be it. So new application. So
Who could take advantage of this right now?
So this is a good question. So for the layer ones, if you want to build a really small layer one that's very powerful, like home stickers, might be feel right. You can use that as the backend for the layer. And you can also use it as an infinite scalable backend for a layer two. Right? And we also added the streamings like the execution support. You can process the transaction by batch, like a block, 20, 30, 30, or you can process it one by one and generate worker boot after every single transactions. And you can have something, like enable something like a real-time blockchain, really small transaction latency blocks.
So what existing blockchains could be?
In theory, all of them. But then, like for the blockchain that has been running for years, right? You will need to have a regenesis of the worker root. So we take some data migration effort. It's basically like migrating from a Merkle tree to a Virgo tree that Ethereum is undergoing right now.
What about chains that don't have trees?
You'll be very straightforward. You just need to port the data over there and up and a certain coin to a half fork of the tree.
Could this keep up with something like Solana?
Definitely. You would definitely not slow down the Solana. And could it make it go even faster? Okay. It depends on the current workload characteristics of Solana, which requires like a deeper dive. But nothing is impossible. Yeah. And I would say it would definitely not slow down Solana, but give them extra property with the full history of the bold Merkle.
And make them more CK friendly.
Yeah. Not just CK friendly, but L2 friendly too. Basically more interoperable.
Is the part right Pokemon classes like Tom Cruise and Truman Cook camera. But anyways, tell us I guess how does this work with ZK? Go into that part. How do you want to feel free to judge?
Yeah. How does it work with ZK? So we ship the code with a status validation example, right? Which you can trivially move that on SP1, like many people are doing with Ref. And then you can easily put an EVM on top of it. And then it can become a very valuable ZK rentee here there too.
Yeah, I mean, I think today when we make a roll up in ZK, there's two parts that are expensive. There's like MPT, which is basically Merkle proving against the Ethereum Merkle partition try, all the story. And then there's actual like the overhead of like the R EVM interpreter. And I actually think verifiable dApps with this architecture solve both problems. So basically like if you have a more efficient DB, you can reduce the overhead from FPT. So if you have a more efficient DB that doesn't do all the crazy RLP stuff, doesn't do all like the crazy node updating stuff, you can have a lot more efficiency gains here. And then for an application, like for example, trading, say the only thing my rollup does is trading. Doesn't make sense to like have to run EVM bytecode and go through the overhead of that in your rollup and prove all that stuff. No, you should just go direct to your application and have that logic in like native RISC-V code. And so I think if you have a better DB that's like more easily verifiable, more efficiently verifiable, and you have an application that just does application logic instead of having a general purpose VM, then you kind of get the best of all worlds where you just have a particular rollup that's doing a very particular function, very efficiently provable. So sure, SP1 can get like 10x better, hopefully, 100x better. But here, I think there's another like, maybe even 100x plus improvements by doing these two things.
Yeah, so if we go back to the first page, so we don't have this blocker, we take out this one, and with all the native implement, like infinitely parallelizable workload, provable workload, and we use compute the storage go. So just like we didn't see any office blocker that prevent Web3 to be more like Web2.
Yeah, I mean, with these taken off the table, these are no longer, none of them are huge blockers. It is now, could be on parity with what exists in Mach 2 today. And you can give that snappy user experience that it is as secure as existing gas space. the pain that we go through for waiting for transactions to confirm doesn't have to exist. It can be smooth, it can be snappy, it can feel like the centralized applications you use today. Yeah. One thing we had talked about to even drive home more why vApps are so important is I'd asked you off camera, what can we do to make proving faster? And you always do what was that? That conversation. So, is it reducing opcodes? Is it reducing? Is it higher, beefier computers, or is it something that you to make them compatible optimization? You gotta
Normally you take wasp code. So this, I don't know, like let A equal B plus C. Then that gets compiled to RISC-V, which is an instruction set where we're executing opcodes like, add something, mul, something, zor, something. So, normal instructions. And then it goes into FP1 and you proving. So if you want to build a verifiable application, there's a few ways to kind of improve it. One is SD1 could just get more convinced. So remember, I think at the beginning I said, when we first launched SD1 in February, it was able to choose through proving, 100,000 cycles per second. And since then, until now, in December, we're now at like 2.5 million cycles per second. So there's kind of this trajectory of SB1 and just able to prove a bunch of RISC-V cycles a lot faster. So, okay, this is kind of our job as a company. Another way, though, you can make your computation more cheap or fast to prove is you can just reduce, at this level, you can reduce the number of cycles. So you reduce number of RISC-V cycles. So if you take the number of cycles you need to prove and go from like 2 million to 200,000, that means your computation got 10x cheaper and faster to prove. And there's a lot of things you could do here. One thing that I think we've been kind of talking about is that instead of deploying Solidity to an EVM and then taking the EVM, running it through something like Ref or Revim, and then proving that in SP1. So that's like the flow most people do today, is like the decentralized application written in Solidity, I compile it to EVM, and then I run a Rust EVM interpreter inside SP1 to prove execution of the dApp. It's like very convoluted. It's like an emulator within an emulator. You can just go direct. So you could just have my application, maybe I'll call my verifiable application, and it just goes directly to SD1 through RISC-V.
Quick question. So we talked about this before. So what kind of reduction are we looking at again from that emulation to that?
It can be really, really significant. We did some very basic studies, and we found that for like computing a Fibonacci number, this was around like millions of cycles when you did it end to end. But in raw SP1, if you just took like computing the Fibonacci number, this ended up being like tens of thousands of cycles.
100x.
So that's like 100x. So I think for the most popular applications that want to be really high throughput, do a lot of computation, you can get 100x from going from general purpose to application specific and having application specific verifiable block space. So that's very exciting. And these things also stack together. Like we get a 10x here, you get 100x here. That's like about.
You get 100x the database. And not compounded.
And not just like reducing the cycles, you can change the workload characteristics. For example, on EVM, right? There are a lot of your DeFi swap or Uniswap, right? So, and that involves, let's say, if we should keep updating the imbalance of the contract, which become a collision port, a hotspot, right?
Yeah.
And it lower the degree of polarization in the workload itself.
Yeah.
But if you were to write your exchange, let's say from scratch, you can carefully design the architecture to get it out from the on day one. So lower cycles, lower again, less, lower number of cycles, less cycles, more realizable.
Yes. Yep.
Yeah. And there's no database blocking you from writing it into this state.
Yeah. Yeah, I think all those things you're saying are true, and like they all snap together. So I think today, like most of the things that are proven with SP1 by volume are just like CK EVMs. And I am hopeful in the future, and it seems like you guys like have kind of independently come to this vision, which is like very, very cool, is like you just have applications that are run in CK that are verifiable. Instead of going to this intermediate layer. And yeah, I think in general, like one thing I've seen in this space is like when a lot of different people come to the same endgame architecture, that convergence indicates there's like some fundamental correctness. Amazing. And I feel like we see that right now with the rollup stuff. Like Solana has network extensions, and like Ethereum has rollups, and Celestia also has like this rollup centric architecture. So I think we are getting this convergence towards decentralized base layer. Everything is verifiable on top of that. And I think, yeah, maybe like the next meta is like going from general purpose block space to app specific block space.
Very cool. So I do love what you said about like taking this stack together. Let's say you have like 100x improvement on one layer, 10x on that. Altogether could be a million x improvement. And then anything could be made possible with that level of innovations.
Please, if you enjoyed this, you'll enjoy the very technical vApp and QMDB paper. That was co-published by LayerZero and Succinct, and then the QMDB paper as well. Both of those combined, we think, help move the space forward in a very meaningful way, where we can get the Web 2 experience that the whole space is converging towards, but in a secure and verifiable manner, which is something that we at LayerZero and at Succinct really value and think where the space needs to go.
Yeah, I think overall I'm most excited to see ZK kind of hit this inflection point in 2025 where it feels like the tech is actually ready. It's very easy to use. And with all this stuff, like we can just make so much more stuff verifiable, so many more applications verifiable, and we can actually like go and prove everything and prove the world software.